Okay, so I'm going to hand back everything, the test, the take-home part, and the in-class part. Um, did you turn anything in? You did? Where'd you turn it in? You did? I need to check. Maybe I got mixed up somewhere. Uh, yes? I did. Yep, I did. Yes. Um, have you ever heard that excuse? The dog ate my homework, right? Is this you? Right. My wife's dog ate your part of your test, but after it was graded. So when I hand these back to you, the strip of paper that you're going to get has some numbers across. Of course, it's going to have your name. The next number you see is your overall grade in the class, your quiz average, which is 15% of your grade, exam 1 average, exam 2 average, exam 3. The way I did exam 3 is a 60-40, whichever was better for you. So if you did better in class, it was 60% of your grade. If you did better at home, it was 60% of your grade, okay? But it was 60-40. And then the last numbers are what you would need basically on the final, because we're pretty much down to the final. So this is pretty much what you would need on the final for an A, a B, and a C. So if this student got a 75, they would get a C, right? Even if they got 100 on the final, they'd get a C. Now, here's what I've done. We're supposed to, I think I have you down for like 8 or 10 quizzes, but we hadn't done that many. So I decided I was going to build a curve into your grade. So for the remaining, I think it was 4 or 5 quizzes, I gave everybody 100s. So that really had a dramatic impact on your grade. Look at it this way. It was basically like adding 30 points to one of your exams, is pretty much what it turned out doing. But with that said, I believe when you look at your grades and stuff, you'll see where you are. We can talk about the final when we get to it. I believe most of you are still within striking range of getting through the class, but I don't know. Each one's individual. So, Aaron, we need to talk. I don't know if I have your other take-home test because I have you down for 0 for it right now. 130. Okay. Yeah, I believe you. Maybe I got it mixed up in here somewhere. Eric, let's see. Who is this? Isaac, uh, Jonathan, John Cortez, Pamela D, Brianna, Sarah Duarte. Okay. Let's see. Mandy, Neil, Neil, Pamela, Pamela D. Sorry, I'd already called you. Rodney, James, Craig, Flavio, Devin. Hey, I had put on here, see me. It's nothing major. I just want to talk to you. It's nothing big. No, I don't want you freaking out about it or anything. Steven Ramirez, Neil, Javier, John Sherman, Pamela Vargas, David Wolford, Julia, Garvey. Yeah, Aaron, I don't, I don't know. What is it? Jarvik. Well, you should have corrected me a long time ago. 60-40. Whichever was higher got 60. Jarvik. I like Mr. Nelson too. That sounds good. Aaron, we'll have to figure it out. I'm going to have to look back in my office. You turn in the mailbox on the desk? Yeah, so I should have got it. So I'll have to go back through and look through my paperwork. Okay. Make sure I didn't accidentally put someone else's work with your work because I'm missing one test. So you might have a lot of questions about the test. Um, I think probably too many questions for me to answer, considering we have material to cover. Um, I had promised you, I had talked about the possibility of like letting you replace your lowest test grade or something like that. But here's what I really think I'm doing. Since I've given you hundreds for like 4 or 5 quizzes, that's already a curve. Um, I think what you'll do is you'll take the final, and then if you'd like to try and bring up one of your test scores, you'll have to tell me after you turn in the final, hey, I want to try and bring up my exam 2 score. And I'm going to hand you like 2 or 3 problems from that exam. It's not going to be a full test, but it's also not going to be able to replace the whole grade. It'll just be able to bump it up maybe, 10 to 20 points. That's about it. Nothing. I'm saying like if you have like a 40 on it, you're only going to be able to get like 20 more points, two letter grades higher. That makes sense? So if you're like right there on the edge right now, being able to pass, and I can't tell you exactly what you need to do the rest of the way. You just need to do well, and then do well again on that other part. Drop date was on Friday. I only had 2 people send me the test by the deadline of Thursday midnight. So those are the only 2 people that I emailed and said, here's where you stand in the class. Everyone else, you had to make that decision for yourself, right? Okay. All right. Any questions? I'll tell you if I want to talk about it now, but any questions about the test? I'll put the answers up. Yep. I just hadn't found one test it was missing, so I didn't want to post the solutions yet, but I'll put them out. Who got number 5 right? Oh, I can almost say except for maybe one person, maybe 2. Did you get 5, Rodney? Number 5. Almost everybody got that number 5 converged. But what do the instructions to the problem say? What does it say? What is it? Is that what it says? Yeah, and what it converges to. Number 5 was a geometric series, and a lot of people were able to determine that it converged using comparison test or ratio test or something like that. But nobody was able, with the exception of like maybe 1 or 2 people. You got it? Huh? What did you say it converged to? 1/4. It doesn't converge to 1/4. Converges, I think, to 1/9. 1/3. And then the other one converges to like 2/9 or I don't know. I'll put the solutions out there. But that's number 5 is an example of a problem where you have a series and you have to rewrite it a r to the n minus 1 and identify what a and r are and then use the formula a over 1 minus r. So a lot of you got convergence correct but didn't tell me what it converged to. I would say that was probably the most missed problem. And then on the integrals, I had said on the integrals, just set them up. Don't evaluate. So a lot of you exhausted a lot of time and energy evaluating integrals that you didn't have to evaluate. And then even at the at-home test, you just had to set them up. So, yeah. Pardon me? It wasn't like test 2, it was just set them up. Yeah. But it was good exercise, right? That look. And then it's obvious that the series, nobody here is has mastered series yet. I mean, it's, and I wouldn't expect it. We covered 8.4 and then had a test 2 days later. So I wouldn't expect you to have mastered that topic yet. But we're going to see a lot more of it now. So if we're going to keep not building on it, we're going to keep needing it. So hopefully as we move on, you'll start to see it a little more. You know, sometimes when you move on to harder stuff, the stuff that you were struggling with becomes the easy stuff now. That's kind of the way it'll be. It's like, we'll see how it goes, all right? Not today. Yes, we will cover Taylor. Are you covering Taylor series in a different class? Okay. Yeah. On Thursday? Yeah, we won't get to it today, or maybe Wednesday. Wednesday we'll get to Taylor series. Oh, John. All right. All right, let me close this out. Now I'm trying to figure out what works best in here. Still haven't figured it out yet. As far as me going through notes. And, I've been sitting here doing like point click type thing where I have everything pre-written. I'm not sure that that's really working. I think y'all have to actually see me work through an example in detail. So what we're going to do here is I'm going to go through these notes. I already have all the problems I want to do today worked out, but once I get to a problem, I'm actually going to open a new page and work it out. All right? But the notes I send out to you, you know how I send out the notes as PDF? It'll have everything all smooth and worked out clean. All right? All right, so we're going to start today power series. And there are going to be some definitions, but those, I'm not going to write down. I'm just going to have them on the board here. So first thing is the definition of a power series. A power series is any series that has this form to it. So it's a series. It's an infinite sum, right? Where does the sum start? This is already something slightly different than what we are used to seeing. For power series, we normally start our series at n equals 0, okay, to infinity. And then what it is c sub n times x to the n. So if we start plugging in values of n, starting with 0, we get c sub 0 x to the 0. What's x to the 0? 1. So we just get the c sub 0 by itself, right? Then you let n be 1. You get c sub 1 x to the 1. Then c sub 2 x to the 2, c sub 3 x to the 3. So this right here is a series. It goes on forever. It's infinite. The major difference in this as compared to what we've been doing is the appearance of x, right? Everything we've been doing before, it's just been like number, and we've been saying, does that converge or diverge? And now we have the variable within the series. All the little c's in front, c sub 0, c sub 1, c sub 2, all of those are just constants. So we've got a bunch of numbers that might be changing in front of a bunch of powers of x. And each time you move to the next term in the series, the power of x goes up, doesn't it? You see why they call it a power series? These are all powers of x, aren't they? It is a series of powers of x. So it is a power series. With me? If we fix x, okay, if we come in here and we replace x with some value, then do you agree that that power series is just a series like what we've been studying? Like if I plug a number in, let's just say I plug in the number 1, 1, 1, 1, then I get c sub 0, c sub 1, c sub 2, c sub 3, c sub 4, and I just get a bunch of numbers? Yes? And that we can look at as, does it converge or diverge from what we did on our last test, right? No, we're never going to agree. Since it's a power, are these mostly to diverge? Nope. You would think maybe because they're powers, but it won't. It's not always the case. Okay. All right, so if, now this is important, all right, if x is a value for which it converges, so like we're free, x is a variable, right? If I plug in a value of x, it may or may not converge. It may converge, may not, right? If the x I plug in causes the series to converge, all right, if it causes the series to converge, then this power series right here is a well-defined function. In other words, I can put an f of x in front of it and call a function this infinite sum. Remember, functions have to be defined, right? You have like domains of functions. So if the x I'm going to plug in here makes that series converge, then I can define a function to be this infinite sum, and then if I plug in a value, like 2, let's say, it should spit out an answer, right? Whatever it converges to. So I have a function that is now the infinite sum of powers of x. And it's like an infinite polynomial. You know how we have like quadratics, cubics, fourth degree polynomials? But those always stopped, right? You had like the highest degree. With the power series, you don't have a highest degree, right? It just keeps going forever. With me? Kind of? We have a function now? All right, so let's take a look at one of the simplest series that we could look at today, and that power series. And that would be if we say, let c sub k be equal to 1. Remember the upside down a meant for all k? Okay, so that means each of those numbers in front of the powers of x is a 1. So my first one here is a 1. Right, I've got my first c here is a 1. The second c in front there is a 1. That one's a 1. That one's a 1. So what do we get? 1 plus x squared plus x cubed forever. That looks like something. See below? Right here? That looks geometric, doesn't it? Isn't it a number, a, plus a number, same number, a, times, now instead of having an x, instead of having an r, what am I using? An x. R squared is like the x squared. R cubed is like the x cubed, isn't it? So isn't this series right here, 1 plus x squared plus x cubed forever, a geometric series? With a being what? 1. And r being x. Well, our question in class today is going to be what values of x make it converge? Now we know right now that with geometric series they converge when? Absolute value of r is less than 1, right? That's what makes a geometric series converge. So this series right here, 1 plus x squared plus x cubed forever, converges if the absolute value of x is less than 1. That's basically us saying absolute value of r less than 1, right? No difference from geometric from last time. Now I put something else here on the side here just to make sure everyone understood how absolute values work. When you say, and I'm going to write this on the board also, when you say the absolute value of x is less than 1, you really mean all x's that are less than 1 and all x's that are greater than negative 1. And in a way you can look at it is like on a number line. Like if this is 0, this is 1, this is negative 1. If I want the absolute value of a number to be less than 1, that means I've got to be within 1 of 0, right? 1 each way. So any x I pick in here, the absolute value of it is smaller than 1, right? So this x must be bigger than what number here? Negative 1, right? And must be less than what number over here? 1. So whenever you see an absolute value less than a number, you set up 2 inequalities. The first one is just drop the absolute value. Boom. The other one, you drop the absolute value, flip the sign, and flip the inequality over and change the sign of what's on the right side. That's what you do to solve an inequality like this. Drop it, flip it, change sign. Those 2 inequalities are the same as this. and that's the same as this. We'll need that later. So if the absolute value of x is less than 1, we're in business. This will converge. If it's greater than or equal to 1, it diverges. And that's we learned that when we learned about geometric series. So there's nothing new from that, right? Any questions? Okay, now we can generalize power series by just making one little change. Remember before it was just c sub n x to the n? That's what it was. Now what I've done is I've thrown in here an x minus a. And x minus a is just x minus a number. So x minus 2, x minus 1, x plus 3, right? Anything, x with a constant here, subtraction. Anytime we have that, we call this the power series about a. The power series about a. So if this was x minus 2, I would say that that is a power series about 2. If it was x plus 2, I would say,
It has to be minus, huh?
well, can you make subtraction? Minus, minus, right? So if that was x plus 2, you could make it power series about negative 2. With me? All right. So again, though, let's take a look at some possibilities here whenever I have this power series about a. What if x is a itself? Okay, so what if remember I said x is a variable. So what if I let x be a? What happens here?
You get 0.
I get 0, don't I? And then I'm basically adding up a bunch of zeros, which basically gives me nothing, right? That means that sum goes to something, doesn't it? It goes to nothing. But that's a number, isn't it 0? So if x is a, this thing converges. What if x isn't a? Then we have to figure out what the hell happens, right? We have to see what happens. All I know is that if I plug in like a here, this sucker's got to converge. If I don't plug in a, I got to see what's going to happen. All right, this is going to be our first example. N factorial x to the n. I'm going to start a new page. N factorial x to the n. The question here is, for what values does this series converge?
Values of x, right?
Yeah, values of x. Sorry, I should put that in there. So now here's the thing. I want you to really understand what's happening here. As n goes to infinity, what happens? The first test we had with series, wasn't it the nth term test? The nth term? So like if I do like nth term here, nth term, let's see. Limit n goes to infinity of n factorial times x to the n, right? That's what I have. Now, let's see if we learned anything. If that goes to 0, what can I say? If this right here, if that limit goes to 0, what can I say? Well, it converges to 0, but what does it say about the sum? I don't know anything, right? The nth term test says if this limit goes to 0, I don't know anything. Now, if it goes to something other than 0, what can I say? This diverges. The sum diverges, right? That's what the nth term test says. That's that same quiz question I gave you, remember? Okay, now what does this go to? N factorial, as n gets bigger, that gets bigger, doesn't it?
Yeah.
X to the n. What is that? What happens there?
That's what you put on the x, though.
I don't know, right? Like,
For a fraction, like 1 over 5.
exactly. If I put 1/5 in here for x, 1/5 to the n gets smaller, doesn't it? Now, if I put 2 in here, 2 to the n, it's going to get huge, right? So it all depends on the x I plug in. Don't you see that? I mean, can you see that? So right here, I would sit here and say, I don't know what happens. I can't even nth term test that because I don't know what x is. For it to what? It looks like it, doesn't it? It looks like if x is bigger than 1, this is going to diverge. Doesn't it look like that? But it can't equal 1? Okay, let's see. How would we attack this? So here's the general approach. We're going to start with the ratio test. The ratio test is used extensively in this section, all right? Ratio test. Now, I expect that you have that ratio test with you. If you don't, you should break it out. What does the ratio test say? You take the limit
As n
and
goes
goes to infinity,
the absolute value of a sub n plus 1 over a over n.
and that this is going to go to some number, right? If we're going to look at that limit right there, the limit of the ratio, the limit of the absolute value of the ratio. And what are my conclusions from ratio test?
N equals 0.
Well, what does it say? If the absolute value of L is less than 1, what? If you take this limit and it's smaller than 1, what happens? What can you tell me about the sum? It converges. What if L is greater than 1? Diverges. What if L is 1? Inconclusive. Now, after the test, I really need to make sure that y'all understand what's happening here. Because we're trying to figure out what happens to this sum, right? An infinite sum. What happens to it? Does it add up to be something or does it go up to infinity, right? That's the question. To figure that out, we set up this test. The test has me doing a limit of a ratio. If that limit of that ratio turns out to be a number that's that's less than 1, then what converges? The sum converges, right? If that limit turns out to be a number bigger than 1, it diverges. It being what? The sum, right? I think that's where I was seeing a lot in the test where people were losing like sight of what the test was leading you to. The test leads you to a conclusion about the original series. That's what it gives you a conclusion for. See, so like, let me give you an example. On the test, someone would have taken this limit and they would get the number 2. And so they would say converges. Because they're saying, oh, well, this goes to 2. It goes somewhere, it converges. That's not what the test says, though. The test says if this goes to a number, then your original series diverges, right? If it goes to 2, it diverges. So we have to keep all of this in perspective. Like, what are we doing? What is the result of our test? Okay, so now I need to set this up. Any questions? Now, A sub n for us in this problem, I should have come back up here. A sub n is this, is the inside of that sum, right? That's our A sub n. So that's A sub n up there. Now let's write out this limit. This is the limit as n goes to infinity of A sub n plus 1. So I'm plugging in n plus 1 everywhere I see an n. N plus 1 factorial, x to the n plus 1. All divided by A sub n, which would be n factorial x to the n. Now notice on this, in class when we were doing the other problems, I was always doing like the fraction over fraction. I would flip it. This wasn't a fraction, right? The original problem was x to the n, n factorial x to the n. So there was no fraction to put on top of a fraction. It was just something on top of something else. Okay, now this is equal to limit n goes to infinity, absolute value. N plus 1 factorial can be rewritten as n plus 1 times n factorial. I've covered that in class several times now, right? This n plus 1 factorial turns into this. Yeah, now this x to the n plus 1 turns into x to the n, what?
Times x.
Times x to the 1, or just x, all over. Now on the bottom, n factorial x to the n. You can cancel out your n factorials and your x to the n's. And so here's where we are. Notice I'm just carrying this limit the whole way, right? I haven't taken a limit, but I'm carrying it this whole time. I have absolute value n plus 1 times what? X. Now, n in the problem, right? N in the problem starts at 0 and goes up, right? So n will never be negative, correct? So I'm going to now write limit n goes to infinity of n plus 1 times the absolute value of x. So basically what I did is I took the absolute value of each of these. The absolute value of n plus 1 is n plus 1. The absolute value of x is the absolute value of x. Now, tell me about this limit as n goes to infinity. What happens to this first piece right here? What happens to n plus 1? It goes to infinity, doesn't it? So what about absolute value of x? That's the one thing we don't know what x is, right? Let's say just x is 1/2. What's going to happen?
Still infinity.
It's still going to be infinite, right? Because you have something going to infinity times 1/2, right? What if x is negative 1/2?
Infinity.
Still infinity because it's an absolute value, so it's the same as plugging in 1/2. What if x is 3?
Infinity faster.
It's going to go even faster, but it's still going to infinity, right? Y'all with me? It looks like no matter what number we choose for x, this thing is converging, or this limit is approaching infinity, isn't it? Except what number? 0, right? If x is 0, not approaching 0, if x is 0, then this doesn't matter, does it?
Indefinite.
N plus 1's gone. It's wiped out. What's that?
Is it an indefinite form?
No, it's not in indeterminate form because even though this is approaching infinity, if I say x is 0, that's different than saying x is approaching 0, right? Indefinite forms or indeterminate forms are when one thing's approaching something the other one's approaching, like infinity over infinity, 0 over 0, 0 times infinity, they're both approaching. But if one of them is 0, it doesn't matter, everything else is dead. So I need to somehow come to some conclusion. If x equals 0, then what happens if x is 0? Then the limit as n goes to infinity of n plus 1 times 0 equals 0, which means what?
Convergence.
What converges?
The zeros.
Why? Because 0 is less than 1, right? That's what we needed to check, remember? That this limit was either one of these three things up here, right? Less than 1, greater than 1, or equal to 1. We got that it was 0. That means it's less than 1, which means the original series converges. Yes? Go ahead.
So for every power series, do you use a ratio test, or can you talk about?
Well, ratio is going to be used a lot. Sometimes root test is used. Sometimes integral test, but normally, like most of the problems we're going to see, it's going to be ratio. Ratio is one of the most important tests that we use. Okay, so this says what now? Less than 1. Therefore, the sum n equals 0 to infinity of n factorial x to the n converges if x equals 0, right? Agreed? If x equals 0. Now, that's just my conclusion from this. What if x wasn't 0? Okay, if x is not 0, that means that that limit goes to infinity, which is greater than 1, right? And if that goes to infinity, then it diverges. Therefore, sum, n equals 1, or sorry, n equals 0 to infinity, n factorial x to the n diverges if x is not equal to 0. And we've covered it all, haven't we? I mean, think about it. X, we've basically come up with the values of x that make this thing converge. What are the values of x that make it converge? 0. Nothing else works. Okay? How is that for a first example?
Okay, I have a question though.
Yes.
But would you have to worry about the combinations of n and x to make it 0?
Wait. Say again. Don't you have to worry about what?
The certain combinations of n and x. So
Not
if we
sure I
take the
follow.
number, so since we start at 0, there will be certain numbers that where x and n will cause it to make it like, so for instance on this problem like 1.
Okay.
N is 1 and x is 1, it would just be 1. And so wouldn't there be certain like x values that cause it to, like say if x was 1 in this case,
Yes.
1 to the n power is always 1.
Okay. So you're saying if x is 1 right here,
Yes.
that's going to be 1. So forget it's even there.
Okay, so okay, but then you're times it by whatever the
N factorial is. Remember, n factorial, you start out at 1, and then you go plus
yeah, yeah,
2 times 1 plus 3 times 1 plus 4 times,
yeah.
sorry, not 4 times
I
1.
got,
You know
I
what
see
I'm saying.
you're saying
Yeah.
there.
And then forever it blows up.
Okay, but will there be that case depending on, the circumstances of n and x?
We've covered it. That's what the ratio test allowed us to do.
Okay.
It allowed us to find some restriction on x
Okay.
that makes the ratio test fail, converge or diverge. Once we have that, everything else doesn't matter. Let's look at another, let's see where we are in my notes here.
So all the ratio test does is make the x absolute value to where it's only going to be positive numbers, right? Like that's the point of the ratio test.
The ratio test is a way of, that's a great question. The ratio test gives us an inequality for x. That's what it gives us. Because we want the ratio test to turn out to be less than 1, don't we? All the time? Or greater than 1? So whatever comes out of our limit part, right? Whatever comes out of this limit part that we had here, all this junk, whatever comes out, we want that to be less than 1. It creates this inequality. Now, it may be just x in here, maybe something else, as the next example is going to show. Okay, there's the problem on the bottom there. I'm going to start a new page for it. For what x, or this should be for what x values does this converge? Sum n equals 1 this time, 1 to infinity of 2x minus 5 to the n over n. So we have sum n equals 1 to infinity 2x minus 5 to the n over n. Let's take a step back just for a second. Let's just say that this was not 2x minus 5. And let's just say it was 5 to the n. Just 5 to the n over n. What would happen to this series? 5 to the n over n. Why?
5 to the n goes faster.
Because the fraction is always going to be bigger and increasing infinitely.
If you did the nth term test, right? You get infinity over infinity, wouldn't you? And then you do L'Hopital's rule one time.
And it would be 5 over 1.
5 to the n times natural log 5 over 1. Because the derivative of 5 to the n is 5 to the n natural log 5. The derivative bottom would be 1. Now you let n go to infinity again, it would go to infinity. Since it doesn't go to 0, it diverges. No? Did I lose everybody there? No? Okay. That's just pointing out if this was a number, we'd be able to figure this out. It's not a number though. X we don't have control over. So we want to know what x's are going to make this thing converge, what are going to make it diverge. So first thing I'm going to do is break out the old ratio test. Ration test.
Did you do the root test for this?
Well, the n on the bottom is not n to the n. If it was n raised to the n, I would think about root test.
You can't
'Cause
like square root, I mean like n root,
nth root of n? Yeah, I suppose you could.
n to the n, square root of n.
You could, I guess you could, yeah. You could do nth root of n all to the n.
Uh-huh.
But I'm not sure. You want to try it yourself? You can. I'm going to stick with the ratio because the ratio should work out pretty clean. Limit n goes to infinity of, let's see, what are we doing? Absolute value. This time I do have a fraction, don't I? So I'm going to replace all my n's with n plus 1s first. 2x minus 5 to the n plus 1 over n plus 1 times, now flip it, a sub n, so it would be what? N over 2x minus 5 to the n. Now I saw some crazy arithmetic on the test, like stuff that I know it happens, but it's just like, that's scary. Like I saw things like this, canceling n's like that. I mean, that's, no, right? No, no. That's how bridges fall. That's how planes fall out of the sky. So be careful with your algebra, okay? What can I do here? I can rewrite that 2x minus 5 as 2x minus 5 to the n times 2x minus 5 to the 1, which you don't need it. And then that's about all. Let me just do that first. Now what cancels here? 2x minus 5 to the n. Does anything else cancel? No. Yes.
Say, can you pull out the n? So it would be n times 1 plus 1 over n.
N times 1, what?
Like on the denominator, n plus 1.
Uh-huh.
Bring out the n.
How can you bring an n out of this? This one doesn't have an n. You would have to have an n in both.
Like we did on the exam problem. Yeah, it would be 1 over n.
You could do something like that, yes.
And when I count out the top end.
Yes. But let me rewrite it first. Let me rewrite it. I think you're on the right track. But I also don't want you getting ahead of yourself here. Okay, watch the way I write this. Do you agree with that? I mean, 2x minus 5 on top is the same as having 2x minus 5 on the side by itself, right? N over n plus 1 is the same as this. And then now, limit n goes to infinity. Now, n is always a positive number, right? So I can say n over n plus 1 times the absolute value of 2x minus 5. Any questions yet? Now, what happens as n goes to infinity now? Infinity over infinity. So one application of L'Hopital's rule would give you 1 over 1, right? Now, you could use, like on that one test problem, you could basically come through and divide everything by n, and you would get the same answer of 1. But L'Hopital is so much quicker, right? I would expect probably for a Cal 2 student finishing this class with a passing grade that anyone in that category should know that the limit of this is 1 without really even having to write anything down. Just that, look, you've done enough L'Hopital rule to know that that goes to 1 as n goes to infinity. Okay, so here's where we're going. This is headed to, now I'm taking the limit. I'm actually letting n go to infinity now, so I no longer have limit, right? This equals what? If that's going to 1, then it's just absolute value of 2x minus 5, right? That's what it's converging to. This limit is converging to that. And what is it that we need for this limit? I mean, this is L, right? This is L, isn't it? That's our limit. So the ratio test says for convergence, we need L to be what? Less than 1. And for divergence, we need it to be greater than 1. So now here's what I'm going to write. For the series, I'm just going to write for the series. Okay, I'm not going to write it all out again. What was it? 2x minus 5. For that series to converge, we need what? What do we need? 2x minus 5, absolute value to be less than 1. That's what the ratio test says, right? Our limit, this, needs to be less than 1 to get convergence. Now, go back over here to where I said if you have an absolute value inequality like this, you can actually set this up by dropping the parentheses and writing out 2 inequalities, right? So this means what? 2x minus 5 must be less than 1, and it means 2x minus 5 must be what? Greater than negative 1. Now let's try and write that out as one string of inequalities. So all that means that negative 1 must be less than 2x minus 5 must be less than 1. Y'all still there? How can you get x by itself here in the middle? Add 5 on, you don't really say add 5 to both sides, you just say add 5 across the inequality. So add 5 to everything, and what happens? You get 4 less than 2x less than 6 by adding 5 straight across. Divide everything by 2. Now you have to be careful with division. Remember with division on inequalities, you flip the inequality over if you ever multiply or divide by a negative, but it's positive 2, so we don't care. So we divide through by 2, less than x less than 3, right? So here's what we're saying right now. If we look at x as a value sitting on a number line, if this is 0, here's 1, here's 2, here's 3. What we're saying is for this series to converge, we need our x value to be where? Somewhere between 2 and 3, right? Anything in here is going to give us convergence. That's a C for convergence. What's going to happen if we pick anything outside 2 and 3? Divergence, right? We're going to have divergence of our original series out there. But what's the missing link? What's the missing piece here that we have not concluded or we have drawn no conclusion for? 2 and 3. What's happening at 2? What's happening at 3? Right? Because what happens at 2? Let's go back up to our limit here. If I plug in 2 right here, what happens? 2 times 2 gives me 4 minus 1. That's absolute value of that is what? 1. And what happens if our L turns out to be 1? Ratio test is inconclusive, right? What if I plug in 3 for x? 6 minus 5 is 1. Absolute value of 1 is 1. L is 1. Inconclusive. So what I can say right now is that, look, I know for sure if I pick a number between 2 and 3, that converges. Anything outside 2 and 3, it converges. Now we must ask the question, what happens at 2 and what happens at 3? Any questions on that? You sure? Still got more to do here. So, what happens at x equals 2 and x equals 3. Question. So I'm going to circle those because that's kind of like I didn't know what was happening at those endpoints. So let's try 2 first. Let, bless you, x equal 2. So what I'm going to do is I'm going to rewrite the original series. I think I'll do this in green just because I feel like I leave green out. Let x equals, let x equal 2. Let's rewrite the original series. It was n equals 1 to infinity, right? Of 2 times x. So 2 times 2 minus 5 to the n all over n. So this is me plugging in 2 for x into the original series. What do I get?
Negative 1 to the n.
Negative 1 to the n. Negative 1 to the n over n.
Alternating harmonic.
Alternating harmonic. And what does an alternating harmonic do?
Divergence.
Good.
I don't know.
50-50, flip a coin. Well, let's act like we didn't know it was alternating harmonic, and we don't remember what alternating harmonic does. This is an alternating series, isn't it? And one test that we do have for alternating series is the alternating series test. So I'm now going to apply the alternating series test to this series. So by the alternating series test, I know I have to show 2 things to show it diverges. First thing I have to do is define an a sub n. A sub n, so we look at this right here, and we look at that as negative 1 to the n times 1 over n, right? That's the way we do an alternating series. We get the part that the sign alternates, and then we peel off the other part, which is 1 over n, and that 1 over n is our a sub n. So a sub n is equal to 1 over n. All right, I have to show what? First part of this. A sub n plus 1 is less than a sub n. That's the first thing you have to show for alternating series test, isn't it? It's the first thing. Is it true? Plug n plus 1 into this. You get 1 over n plus 1 less than 1 over n. Is that true? Yes. We don't need to check that, right? I mean, that's obvious, hopefully. What's the second thing we have to show for the alternating series test? Limit n goes to infinity of a sub n equals 0. So what is the limit as n goes to infinity of 1 over n? Is 1 over infinity, which goes to 0. Therefore, I have shown the 2 things you need for alternating series. My conclusion is it converges. If these 2 things are true, then that alternating series converges. So therefore, sum n equals 1 to infinity of negative 1 to the n over n converges. Which means that back in the big picture of things, I was trying to figure out what happened to this series I started with, the question I started with, right? And I was trying to figure out what happens if I let that one little x be 2. If I let x be 2, it turned into this alternating harmonic, which converged. So now I can go back up to this picture right here, right? And I said at 2, I don't know what happens. And fill it in with which color, purple or blue? Purple. Because purple is for convergence, right? At 2, it converges. So I know at 2 it converges. I still need to figure out what happens where?
3.
At 3.
So it should be harmonic though.
Yeah, this one's going to be a little cleaner. So now, I told you that you would still need the stuff we did last time. You see how we're using it here? Now I let x be 3. The original series turns into 2 times 3 minus 5 to the n over n, which is sum n equals 1 to infinity of 1 to the n, but what's 1 to any power? 1. So just 1 over n, and that's harmonic, right? Without having to do any work. And all harmonics diverge, right? Harmonic diverges. So that means that if I go back up to my number line way the hell up here, I can fill in the 3 up here with what? What's going to happen at 3? It diverges, right? So I can fill it in with the light blue. Yes? So now I'm going to summarize it all right? Here's my final answer. The final answer is, therefore, my series that I started with, n equals 1 to infinity of 2x minus 5 to the n all over n, converges on the interval bracket 2 to 3 open parentheses. Remember, that's how we do it. You don't need this, but remember on a number line, if you want to go from 2, everything between 2 and 3, and you want to include 2, you use a bracket on the interval. You want to not include 3, use a parenthesis. Yes?
You wouldn't use the x notation as like 2 is,
Okay, good question. Let me show you a couple of different ways you could write this answer. You could say x is an element of 2 to 3. You could write x is bigger than or equal to 2, less than 3.
that's what I'm going.
That's acceptable also.
Because that's what we're evaluating the x values.
Mm-hmm. You could get real precise, like a mathematician would do it, and do the set of x such that 2 is less than x is less than 3. That's called set notation. It's all x values that satisfy this condition. But notice, I mean, like on this, you have to use the strict equality here. I mean, inequality and then strict inequality here. Strictly less than 3, but I can be greater than or equal to 2. So there's a lot happening here, right? You have one problem. That problem, we use the ratio test to come up with some idea of what's happening with our x. And then from that x, we have to look at what we get. We got an interval here, and then we have to always look at those endpoints. And those 2 endpoint problems became basically 2 new series from what we'd done before. Make sense? Questions? Comments? All right, that's me working through all that. All right, here's another one we're going to do. For those of you who are going to be engineers, you'll become intimately acquainted with this function. It's called a Bessel function. Bessel functions are good at modeling, like if you hit a drum, right? You get something, you hit a drum, and there's actually ripples on the surface of the drum. A Bessel function is good at modeling what those ripples look like. It's almost like sine curves that are like the amplitudes changing as you go out to the edge of the drum. Also, it's good for modeling heat distribution. Like if you have like, let's say like a DVD or a disk or something that they use for like processors, microprocessors. You have a disk, you heat it, and it describes how the heat actually dissipates out through the disk. Bessel function is good at modeling that. But there's some stuff in here that's kind of confusing, all right? So let's Let's first write it all down, all right? And get the notation right. Remember I said that if the series converges, you can write it f of x, f of x. Well, j, capital J sub 0 is, the J is for the first name of the Bessel guy, I forget his first name. J sub 0 is what we call an order 0 Bessel function. There's a J1, there's a J2. I mean, there's higher order Bessel functions. This is the order 0 Bessel function. So if I plug in an x, right? If I plug in an x in here, I should be able to figure out if it converges or diverges. So the question is, find the domain of this function. That means tell me what x values make this thing converge. So I put it in blue here. The x's for which this series converges. Okay, here comes my new page. Sum n equals 0 to infinity, negative 1 to the n, x to the what, 2n? Over 2 to the 2n, n factorial to the squared. Okay, that's it right there. Everyone got that? So we want to know for what x values this converges. So ratio test. Ratio. Let's try it out. Limit n goes to infinity. All right, I'm going to have some fractions here. So what do you think about the negative 1 to the n? Absolute value is going to kill it off, isn't it? So I'm not even going to worry about it anymore. All right? Negative 1 to the n is gone. How about x to the 2n? I saw this on the test too. You got to be careful. That's x to the 2 times n plus 1, isn't it? Like that 2 is going to have to distribute to both the n and the 1. Over 2 to the same thing, 2 times n plus 1. Then n plus 1 factorial squared. So all I've done is I've taken the original series, taken the sequence inside, and I've rewritten it, replacing all my n's with n plus 1s. Is that okay? Now I've got to do flipped over the original one. So 2 to the 2n, n factorial squared. What else? Over x to the 2n. And again, I'm not going to care about the negative 1. Okay, so on the first one, I'm going to put a little note here. What is 2 times n plus 1? It's 2n plus 2? So can't I split this up to be an x to the what? Times x to the second, right? So x to the 2n times x squared over 2 to the 2n times 2 to the 2. Same reason, right? That 2 times n plus 1 becomes 2n plus 2. If you feel like you're buried in like math right now, I mean this is it. This is what it's all about, okay? This sort of thing. Manipulation of things like this. What's next? Okay, I'm going to do this on the side so everyone's clear. What we're doing is we're taking n plus 1 factorial, right? And we are squaring it. Isn't that what we're doing? Okay, so that's the same as peeling off an n plus 1 and then the n factorial next to it and then squaring that, right? And if you square two things that are being multiplied, you square each one, don't you? So that's n plus 1 squared times n factorial squared. So this bottom piece down here is n plus 1 squared times n factorial squared times, now the other side there's nothing to do, right? 2 to the 2n, n factorial squared, x to the 2n. And I should get some nice cancellation there, shouldn't I? Yeah, things are going to be nice. So what goes away? X to the 2n, right? 2 to the 2n, n factorial squared. Damn, life is good.
Love it.
Okay, absolute value. What's left on top?
X squared.
X squared. What's left on the bottom? 4 times n plus 1 squared.
Two squared, right?
Are we good? We could do that. We could also, just watch this. This is 1 over 4 times n plus 1 squared times x squared, absolute value of x squared, isn't it?
Oh, because all n are gonna be positive, right?
You don't have to have the x,
That's right. I don't need the absolute value. Why?
because
All n's
anything
are positive.
squared is positive.
Yep. So the x squared is not going to matter because no matter what, this is going to be a positive number, right? All right. So what? Let n go to infinity. What do you get?
0 times something.
0. So 1 over 4 n plus 1 squared. Right? This right here goes where? That goes to 0, right? 0 times anything, right? Doesn't matter because, look, this x squared, right? It could be 0, couldn't it? But if it's 0, 0 times 0 is going to be 0, right? What if I plug in like 100? 100 squared is a big number, but who cares? Because this thing in front of it is going to 0.
What did you put infinity?
Well, x can't be infinity. X has to be a real number. Okay, so x is something you fix it, done. So if you plug in a billion, cajillion, gazillion, doesn't matter. The one in front of it is going to get small enough to wipe it out eventually. Because that one's getting small, like approaching 0, never stops. If you fix x to be a number, then you have a constant over something going to infinity. And that's it. It's over after that. Okay, so this limit goes to what? This limit goes to 0, regardless of x, right? Regardless of x. And because it goes to 0, and 0 is less than 1, right? Because remember, that's our L, isn't it? Our L is less than 1. By the ratio test, our conclusion is that what? It being the original problem, right? The original. So I can conclude, therefore, the original Bessel function, I'm not going to write it all out. The order 0 Bessel function, which is that sum, right, converges for every x. Which means you can plug any x you want into the Bessel function, can't you? Which means the domain of that function is what? All real numbers. Therefore, the domain is R, or if you like, negative infinity to infinity. We've actually seen something you probably don't even realize it's happened, but in the first problem, right, that I did, if you can remember this, if you wrote it down, the only value of x that made it converge was 0, right? In the second problem I did, this is the third one we've done, right? The second one I did, it was an interval, wasn't it? It was like everything from 2 to 3. And in the third example, it's everything, right? And it turns out that those are the only three things it can ever be. It can only be a single point, an interval, or everything. You can't have convergence on multiple intervals. Like you can't converge from like 2 to 3 and 5 to 10 and 100 to infinity. It can only be a single point, one interval, or everything. Those are the only possibilities. And it's beyond the scope of this class to prove that, which is why it appears as a theorem. And there's the theorem. This is all in the book. You don't need to write this down, okay? But there is some language in here. So if we're given a power series, okay, any power series, there are three possibilities for what can happen. It converges when x equals a. That means when these two numbers are the same, which we already showed that, right? When x was a. It converges for all x, which was negative infinity to infinity, or it converges on an interval, okay? Now, I need to talk about this case 3 in a little more detail. You know how like over here on the board we had absolute value of x is less than 1? And in the problem we did a little while ago, it was like 2x minus 5 was less than 1. Remember? You'll always come up with an inequality where something's less than r. That capital R is called the radius of convergence. And then the interval that we come up with, like x goes from 2 to 3, is called the interval of convergence. So those are the three possibilities. Also, something to note is that when you have an interval, okay, whenever your power series converges on an interval, there's four possibilities of what the interval can look like. You can have closed interval. That means what? Both endpoints make it converge also, right? You could have this case where one left endpoint doesn't make it converge, but the right one does. Or you could have the third case, like the one we did, 2 to 3, where the 2 worked but the 3 didn't. Or you could have neither endpoint works, in which case it would be a completely open interval. So this is called a closed interval. The one at the end is called an open interval. And sometimes we call these half open, half closed. So look at this question here, and we're going to do this one. Find the radius of convergence, and the interval of convergence of this power series. Negative 5 to the n, x to the n over root n plus 1. Yeah, we're going to do it. Sum n equals 0 to infinity, negative 1 to the n, x to the n over square root n plus 1. All right, before I start this, any feedback? I mean, what do y'all think about this? Is this at all like making the stuff you did before come out a little bit, or no? Is it all just this is more crap piled upon confusing crap? Okay, yeah, and I'm hoping you're even gonna like this more when we get to the next class, because eventually what we're trying to get at is, well, we're trying to build up to what Newton discovered, which was that you can rewrite a lot of functions in math using power series. Like I just showed you that you can look at these as functions, right? So we're getting to the point where we're going to rewrite functions as power series. And then when it comes to integrating and differentiating them, all we have to do is integrate each term of the series. So imagine, or differentiate. Imagine I ask you to differentiate the one I had up here earlier. 1 plus x squared plus x cubed. And this goes forever, right? What's the derivative of this? 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th plus 6x. And that goes forever also, right? That's a new function, isn't it? That's the derivative of this one. What's the antiderivative of this function?
1 plus 1/2 x squared.
X plus 1/2 x squared plus 1/3 x cubed plus 1/4 x to the 4th, right? You see what I'm saying? So what we still don't have and what we're going to get is how do I take a function like e to the x and turn it into its power series? Or take a function like sine x. How do you turn it into its power series? We're almost there. Because once you get there, then you can integrate and differentiate pretty much everything. There's like really nothing you can't do.
You said that's why he was so much better than the other person.
Yes.
Trying to do calculus?
Yes. Plus, this is the way a computer and a calculator works. Your calculator has no idea what sine x is. It knows what the power series representation of sine is. Because your calculator can add, subtract, basically multiply. That's it. So if you have sine x, your calculator doesn't know what the hell sine x is. But if sine x turns out to be 1 plus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial, which is what it is, then, hold on, take out the 1 in the front. Then your calculator can compute sine of 2 by just replacing all the x's with 2's. And it knows it converges and it gets the answer. I mean, there's a lot more we got to do, but we're getting there. We're almost there. Okay, I want to know the radius of convergence and the interval of convergence, which basically means I need to know for what values of x this thing converges, if it even does. So we've been using the ratio test. We like it. It seems very useful. I'm never going to get that. I don't know why I always put that. All right, limit n goes to infinity. Absolute value. I don't need to consider the negative 1 to the n. Hey, was it negative 1? I thought it was negative 5 also. Wasn't it negative 5? Thank you. Change that. Oops. That was a negative 5 to the n. Now that does matter. Now it does matter. Because when I take the absolute value, it's not just going to be a 1, it's going to be a what? 5 to the n. So it does matter here. So I'm going to write this down as, I'm just going to write down as negative 5 to the n plus 1. And then x to the n plus 1 over square root of n plus 2, right? N plus 1 is n plus 2 times the reciprocal, which, and I don't add 1 this time. Could rewrite what? How? Yes, but that doesn't allow you to cancel though. Because it would all be under a root. You would have square root of n plus 1 plus 1, and then over here times on the top square root of n plus 1. You cannot separate these two. Multiplication, you can split them off into 2, but addition, you can't. All right, so we have what here? Negative 5 to the n times negative 5 times x to the n times x all over square root n plus 2 times square root n plus 1 over negative 5 to the n x to the n. You should be getting some good canceling to happen, right? It's like a broken record at this point. Negative 5 to the n, x to the n. Well, anything else? No? All right. How about now doing some absolute value? The absolute value of negative 5 is going to be 5, right? Square root of n plus 1 over square root of n plus 2. Watch the way I write this. So if I have a root on top and a root on bottom, I can put them over each other and then put them underneath the same root, right?
What about the x?
And now the x. So the x needs to be tacked on the end as an absolute value of x, right? Agreed? Now all the Cal 2 students that plan on passing should know what the limit of this is. That's 1, right? Square root of 1 is 1. So we have 5 times 1 when we take this limit times square root of x. So isn't there just 5 root x when we take the limit? Why did I say root? Yeah, I don't know. 5 times 1 times the absolute value of x. That's your limit. When n goes to infinity, that's what you get. Now, because we did ratio test, we need for this to be what? We need, for convergence, we need what? We need that to be less than 1, right? Which means we need the absolute value of x to be less than 1/5. Okay, now right here at this point is where you can determine your capital R, which is your radius of convergence, 1/5.
That's r.
Capital R, therefore, capital R equals 1/5. That's the radius of convergence.
We have to find out what happens at 1/5 now.
Yeah, we still have a long way to go. Convergence. Okay, that's our radius of convergence. Now we need to set up to figure out the interval of convergence. To find the interval of convergence, what we do is we take this inequality here and we break it up into the two inequalities and then write them all as a string. Right? We did that earlier over there on the board with the square root of x less than 1. So now we have that x must be bigger than negative root 5. What? X must be bigger than negative 1/5. And x must be less than 1/5. Did you put something in here?
You're not running coffee this time.
Turn my back and Julie's dropping stuff in here. Yeah, I need more. So what does this mean? Is this our interval?
No, we have to test.
Yeah, what we know right now is this thing's going to converge inside there, right? The question is the endpoint still. We still don't know what happens at the end of that interval. So that's not our answer as far as the interval of convergence. We know that outside of it, we know it diverges. We know inside it converges, but at the ends, we don't know. At those two values. So again, if we were drawing a number line, if this were 1/5 and this were negative 1/5, and we use the purplish one, we know in here it converges. We know on the outside it diverges, but we don't know what's happening here yet. We are going to figure it out by doing what? Okay, let, first of all, x be what? Negative 1/5, right? We'll start with negative 1/5. And what do you plug that into? The original series, right? Let's see, sum n equals, I forgot what it was, 0 to infinity, negative 5 to the n, then x to the n, right? Negative 1/5 to the n, all over square root of n plus 1. Now negative 5 to the n times negative 1/5 to the n means you can put both of those together and make them both to the n, right? But what's negative 5 times negative 1/5? 1. And what's 1 to any power? 1. So this is the same as sum n equals 0 to infinity of 1 over the square root of n plus 1. What happens to that series? Why? So? No, this is important. You can't keep making that mistake. Just because this goes to 0 doesn't mean anything.
You can do the.
If that's how this section would be so simple if that's what it was. If all that happened is you look at that and say, oh, if that goes 0, it converges. If it goes 0, you don't know. If it goes to something other than 0, you know it diverges. So you could try nth term test. The inside of that goes 0. We don't know. So then what? Can't do alternating series test. Comparison, what do you want to compare it with?
1 over n.
1 over n?
Yeah, because n diverges.
Okay, so what does comparison test say? If I can come up with another series that I know what it does and show that that series is somehow connected to that one, then I can, whatever one does, the other one has to do. All right, let me try it. Let me try by comparison.
He's doing it in red.
By comparison, the a sub n that I have is 1 over the square root of n plus 1, right? What would you like to compare it to? B sub n is 1 over n? Is that what you want to use?
I mean, if that diverges, it doesn't prove anything.
Oh, does that mean less, right?
If what diverges?
B sub n diverges, doesn't prove anything. B sub n.
Well, let's keep going with this because this is one of those things not enough of you demonstrated on the test how to do this, okay? So I'm not saying you. I'm just saying,
Would it be the square root of n? That would be n.
you want to change your b sub n now?
Yeah.
Okay, can I stick with 1 over n just to show people why it's not going to work? Okay. If you try and set up the inequality right now, what's the relationship between these two? Which one is bigger? Which one of these is bigger?
B sub n.
The one on the right? Why?
Because it has the denominator is smaller.
N is smaller than the square root of n plus 1?
I mean, greater.
Sometimes this one's bigger than this one, sometimes that one's bigger than that one. It depends, right? So maybe not the best choice, but then you rethought it and you said square root of n. Now which one is bigger? The one on the right's bigger? Because the denominator under here is bigger, that means this ratio is smaller than this one. Any questions? That tells you, wait, which one was bigger? The one on the right? This one like this? So what now?
I was saying, would it still diverge by P series?
Well, what happens to this? Now, remember, we're saying, what happens to this series? This is what type of series? P series with P being 1/2. What do P series do if P is 1/2? They diverge. That means this right side goes to infinity. And that left side is our sum that we're trying to figure out, right? So our sum is less than or equal to infinity, which tells us nothing. Right? That tells us nothing. This is very similar to a problem on the test.
Yeah, no, that's the one.
Yeah, but wasn't the last one on the test alternating? Or
Yeah, it was also.
yeah, the one on the test was just like this. Well, very similar, but it was an alternating series, so we could do the alternating series test.
Can you do that one on the next one on 1/5?
On 1/5?
When you do the other.
Yeah, we'll get to that one. Yep, that'll be alternating. So, any ideas? You want to try ratio on that? I'm not saying not to, but if you do ratio, you have to do what? Let's try it. You want to do ratio? We'll try ratio. So let's get rid of this. Let's try ratio.
I told you I have to change it.
So we're doing a ratio within a ratio. I did it again. So limit n goes to infinity. Absolute value a sub n plus 1 is 1 over the square root of n plus 2, isn't it? Over 1 over the square root of n plus 1, which turns out to be limit n goes to infinity. You can flip them. Square root of n plus 1 over square root of n plus 2, right? And then you can put them both underneath the same root, and that goes to what?
Infinity. Oh,
1
1.
after L'Hopital, right? And what happens in a ratio test if you get 1? It's inconclusive. That equals 1. All right? No go? What next? Integral. Integral test. This is a good problem. So let's try integral. How about the integral test? Now, I noticed this again on the test, and you lost a lot of points on this if you didn't do it right. Integral test says you have to take the original thing you're looking at, which was sum 1 over square root of n plus 1, right? You need to look at that as a function 1 over square root of x plus 1. And you need to show what? F is continuous. Is it continuous? On 1 to infinity. The only thing that's going to mess up this function is negative 1, right? So other than that, it's well defined. So it is continuous. Okay? Is f decreasing? You have to take the derivative, don't you? So let me look at this function f and rewrite it as x minus 1 to what power? Negative 1/2. That's just bringing this up. I'm preparing it for differentiation. Here's my derivative. Negative 1/2 x to the what? X plus 1 to the negative 3/2, right? I'm differentiating, not integrating. This is the same as negative 1 over 2 square root of x plus 1 cubed, right? What can you tell me about this? The denominator is always positive, right? Because I'm taking something cubed, I'm taking a square root, and the thing in here always has to be positive because I'm plugging in x is 1 to infinity. So my denominator is always positive, my numerator is always negative. Negative over positive is negative. If a derivative is negative, that means the function is going down. That means the original function is decreasing. So because that's negative, my function is decreasing. Anything else we need for integral test? Oh, it has to be positive. The function has to be positive. Is this function always here over here always positive?
Yes.
Yeah, as long as you're plugging in positive values of x. The square root of a positive number is positive. Positive on top, positive on bottom. We're good. So f is positive. Now you're allowed to use the integral test. And the integral test says whatever the integral of that from 1 to infinity is, whatever that does, the original one does.
What does it mean when it says readily? Like,
Is what?
it has to be ready to be integrated? Like, what do you mean by that?
Ready? Did I say ready?
Well,
On the differentiation?
on the notes it said it had to be, like, readily like,
Readily integrable?
uh-huh.
In the book it said that?
On your notes.
Did I write that down somewhere? I'll look at it in a second. Let's not lose our train of thought here. I need to integrate this function, right? I need to integrate this. I need to integrate x plus 1 to the negative 1/2 dx. Now I'm integrating, not... Okay, what I meant by readily was that it's something you want to integrate, that you can integrate it, you know? Like, you don't want to pick a problem and say, I'm going to do integral test, and you have no idea how to integrate it. It has to be something that's readily integrable. It's ready to go. Like, it's an integral that you're like, I got it, knock it out quick, you know? Like this one. What's the antiderivative of this? I could do a basic u substitution, but hopefully you're past that. This is just power rule backwards. Let's see. 2 x plus 1 to the 1/2. Evaluate it from 1 to infinity. Just check with me that that's the correct antiderivative. Take the derivative of this. 1/2 comes out, hits the 2, becomes 1. This to the negative 1/2, which is this. And that's the original function, 1 over square root of x plus 1. Now plug in infinity. Infinity plus 1, infinity, square root of infinity, infinity, 2 times infinity, infinity, minus, plug in 1, I get some number, I don't care, that's infinite, isn't it? And now I can conclude this integral is infinite, and the integral test says that if the integral diverges, which it does, right? Going to infinity means the integral diverges, then the sum does. What's that?
Only for negative 1/5.
Yeah, only for negative 1/5. So if x equals negative 1/5, the sum n equals 0 to infinity of negative 1 to the n, x to the n, all over square root n plus 1. What did it do? Diverges? So back up at my number line, which is way the hell up here. I know that at negative 1/5, I should fill it in with that light blue, right? Because it's going to diverge there. Do we have enough time to check the other one? I think we do. If x is now, what am I checking? 1/5. Go into that sum. N equals 0 to infinity. Negative 5 to the n times 1/5 to the n all over square root n plus 1. Which turns into, if you put those two together, what happens? Don't you get negative 1 instead to the n? Over square root n plus 1. Now, this is an alternating series, so I can use the alternating series test, which, man, that test is so much nicer, isn't it? Alternating series test. What's the a sub n I'm going to use? 1 over root n plus 1. What's the first thing I have to show? A sub n plus 1 is less than a sub n. 1 over root n plus 2 is less than 1 over root n plus 1. Clearly, right? Next thing I need to show, limit n goes to infinity. A sub n must equal what? 0. Does it? Yes. Therefore what? That series converges, right? I'm ready for my final answer. Therefore, sum n equals 1 to infinity, negative 5 to the n, x to the n, all over square root n plus 1, has an r of 1/5, a radius of convergence of 1/5, and the interval of convergence is what? Open parentheses, negative 1/5, 1/5, close parentheses. If you don't like that, you can do negative 1/5 less than, right? X less than or equal to 1/5. Hold on now. I'll call you right back. Okay, homework. Pardon me? n equals 0. Oh, yeah, I changed it to 1. Sorry about that. Let me make sure that I didn't miss something here.
Like a mistake or something.
No, no. No, just that there weren't any more examples in that section that I wanted to do. Okay, for your homework for this section, power series, and I recommend you do these problems before we meet again. 3 through, let's just go with 3 through 15 odd. 3 through 15 odd. This is page 469. 3 through 15 odd. Have fun. Let me turn all this off.